So ready to go.
All right. So, good morning, world, and welcome to our STEMMOS webinar for today. And my name is Gernot Grömer. I am the director of the Austrian Space Forum. I'm also an analog astronaut. And I would like to give you a behind the scenes look to an actual spacesuit laboratory. So you will get to see something virtually that is quite unusual and quite exceptional. We usually don't invite people in our laboratory because there's lots of high-tech stuff going on here. But today we make an exception for you, and we are thrilled to have you here at the premises here in Austria, in Innsbruck. It's a rainy, gray day, which is a perfect day for getting a sight into what we are doing here research-wise. So today we will be focusing on the topic of Mars exploration. So technical questions, how can we put humans on the red planet within the next 20 to 30 years, which actually means that the very first human to walk on Mars is already born and might be sitting in the virtual audience right now. So I'm thrilled to especially welcome that very person, although they don't know nothing about their future careers yet, I guess. So what we're going to do is, I would first like to give you a brief introduction to the topic of Mars, as you have some basic idea about what the planet is about, why we're going there, talk a little bit about the Mars simulations we do in the Austrian Space Forum, so you have a little bit of a context of what you're going to see in the laboratory. And if everything works out according to plan, we will also take a close look into one of the laboratories where we actually manufacture satellite hardware. So we'll dressing into the clean room gown, and we'll move into another location than here. So if I do this correct, I should be able to share the screen in a moment. Let's see if this works out. And there we go. And you should now see in a moment now the actual starting slide of my presentation. Maybe somebody can give me a thumbs up. Thank you very much. All right, so let's have a look at Mars from the Earth perspective. Well, first of all, Mars is far away, about 380 million kilometers. That means a signal from Earth to Mars takes on average roughly 10 minutes, can be up to more than 20 minutes actually. So if people are living on Mars and have a problem and they say, Houston, we have a problem, the famous phrase, it will take more than 20 minutes for the reply saying, well, yeah, what exactly? So small talk for Mars is something really critical and not really useful in a way. So when we take a look at the planet itself, it's about half the size of the Earth. It has polar caps comprised of water ice and carbon dioxide ice. It has impact craters like we know from the moon. It has volcanoes. It has a not totally dead geology. There's a few things happening there right now. But most importantly, it is nowadays a dry, barren, cold desert, minus 70 degrees average temperature, an atmospheric pressure of below 1% of what we have on the Earth, a really inhospitable place, no magnetic field, no significant atmosphere, not a very efficient shielding from cosmic radiation. So why the hell are we trying to get there with so much resource and so much infrastructure? Well, the reason is in the past of the red planet. We now know it's a cold, barren desert, but it was not like this for a long time. So we know until like 3.5 billion years ago, Mars had liquid water on the surface, a much higher atmospheric pressure, higher temperatures. It was much more like the Earth. It had oceans down to a depth of 3 kilometers. You could go deep sea diving on the red planet many years ago. And we still see some of those traces of the water. You see here, we call this sedimentary layers. When you have a lake and it's depositing particles that are sinking down, they create layers. It's like, for geologists, it's like a pages of a book that tells us about the past. And what this book tells us is it was much more life-friendly for about almost 1 billion years. And that brings us to the most important question we have in Mars exploration. And that is, was there ever a moment when the spark of life was ever triggered there? Was there ever a moment when their little microbes were starting to grow, bacteria maybe or so? And the honest answer at this moment, if you ask me right now, we don't know it. But that's exactly what science is about. It's about finding out those answers. And the great privilege we have here is that after 30,000 generations of our existence as a species, as Homo sapiens sapiens, we're the first generation to have the technical means to go there and have a look. But the question is, what are we looking for? Like, what is the traces we're hoping to find? And so the first ones we're going to send to Mars, we are sending to Mars right now, are robots. Since decades, we are sending every couple of years rovers there with more advanced technology that help us to understand the early environment, so that once humans arrive there, we have a very good understanding where to take that look. And that includes, of course, cutting edge technology. We have flying objects to Mars, the first aerial vehicle, the Ingenuity helicopter that flew a couple of years ago already. So it is really picking up pace, which means we need humans to follow the rover tracks of the robotic vehicles. And this is exactly what we're doing right now. So this is the work I'm involved. It's the work also Dr. Seda Özdemir is involved with. We are simulating right now already how to do this type of research. How can we look for diminutive traces of life on the red planet? And that means we need to bring not only spaceships and the humans, we need to have habitat structures. We need power supplies, how to feed the people, how to make sure they get air to breathe, how to walk outside in the spacesuit. And that's what we're doing here. We are basically developing spacesuit simulators that are able to mimic all the limitations that are pertinent to the flight-worthy suits then in 20 to 30 years or so. So if your colleagues, in that case, from Italy and from the Netherlands, who are just doing what we call the donning, doing on a spacesuit, we'll see a little bit more about this in a few minutes. And then we take those spacesuit simulators and put them under very harsh conditions. For instance, we freeze them down to minus 110 degrees Celsius in a cryo chamber to see if our thermal control system really works, if the heating is working properly, right? And good thing is, it works. We know that now in the laboratory. We also know there are, there are dust particles on Mars that are also very abrasive, that have electrostatic charging properties that are quite surprising. So it's dust and sand is the natural enemy of the astronaut on Mars. It's not the little green man, it's really the dust, basically. So this can be charging up because everybody who is spending some vacation in a desert-like environment knows it. At the end of the day, when you come home, you're sometimes really so electrostatically charged that when you touch the handle of the door of your hotel room, it sometimes zaps you with a bzzz, and you get this little electroshock. That's exactly what happens during dust devils as well. So when there is dust devils, these little micro tornadoes on Mars that are lifting up the little particles, they can be charging up and they can discharge that electricity with lightning strikes. So we need to make the spacesuit lightning strike proof. Now, that's something you don't need on the International Space Station. That's something you don't need for the Space Shuttle or so. That's something you need for Mars and to some extent also for the Moon. And so we are taking those tests so we know the suits would function with this perspective also on Mars. And then we take into the field. We take to the places that are as Mars-like as possible. And I can tell you there are some fantastic locations across our own planet that allows us to study those behaviors and the workflows there when we combine robots and instruments and the humans together as a consortium, so to say, to really do the science in an efficient way. So we go to places like Armenia, we go to Northern Sahara, we go to Oman, like in this case. I give an example of a mission we had a couple of years ago in a place that looks so much like Mars that it's quite astounding. The picture on top was taken on the 15th of February 2018, and the picture below was taken just 2 weeks afterwards on Mars. So if you ignore the color of the sky, it could be quite convincing that this is actually another world, so to say. So you do a lot of preparations. And for those missions, we typically have 200, 250 people from 20, 25 plus nations involved that train months before this actual mission. We have a station that is being built right in the Mars-like desert, in this case, again, in Oman, that help us to mimic the daily lives of the astronauts what it would look like on the red planet. And when we go outside in those simulations, of course, we have to wear the spacesuits, otherwise it would be not really healthy. And all of this is being directed and being coordinated from Earth, where we call it previously Mission Control Center, but because of the time delay, there's not much of a control you can do. You can do suggestions, you can do a consulting, so to say, and that's the reason why we call this the Mission Support Center. And this is one of the rooms we are using. This is the flight control room of one of those Amadi class missions, and this is one of those facilities. There's more rooms like this that help us to coordinate understand the telemetry from the field, help us to coordinate the workflow. So it's quite a machinery behind this. And I want to show you this before we go into the laboratory to make sure that you have a little bit of a context of what we're doing. One of the things, and this is the first thing I'm going to show you, first with a little video, like a few seconds only, and then we see this in reality, is because Mars is smaller, it has a lower mass. And because it has a lower mass, it is lower gravity, roughly 1/3 of the gravity level we have on Earth, like 38% or so. That means if you can jump 1 meter on Earth, and that's something you can do with a little bit of training, you can jump 3 meters on Mars. And that means the physiological workload you have as a human on the red planet, that's smaller as well. And that makes a few things, let's say, different, not always easier, but different. And so how can we do this on Earth now? Because, we cannot switch off gravity. There is no isolation matrix that blocks gravity. I wish we had that sometimes, but obviously we don't. So we have to improvise. And with a little bit of clever work, we have been installing a machine that allows us to replicate the workloads of walking on Mars here on Earth. And that's called the Vertical Treadmill facility. It's like, think of a fitness studio, but with much cooler settings. I'll show a quick video of this. Basically, what you're going to see is a human in suspension in the horizontal that is pulled against a machine that is like a treadmill, like from a sports fitness studio, for instance. And depending on the pulling factor, you have more or less gravity. And when we do this for lunar gravity, for instance, that's a little bit more easy to see. This is what it looks like. And with some luck, you should be able to see a video. Ignore the sound, that's not important here. That's one of our analog astronauts, Dr. Wald, who is from Austria. He's a physicist, actually, who underwent all the training. And this is not a slow motion video. This is in real time. This is actually what it looks like when you're walking on the moon, and it's somewhere similar when you walk on Mars. The moon is 1/7 of the gravity level, Mars roughly 1/3. So this is really something that mimics the movements of humans on, in this case, on the moon. So having said that, I would like to move on and basically stop the sharing for a moment. And I have a colleague with me, Sindre Brandt, who is my assistant, and she's our camera lady for today. And with some luck, we should have a second video being activated any moment now. So I will go dark here for a second. And there she comes. And there we are. Hi, Selina. So we're walking out from the office right now, obviously. And we go right into the laboratory area in the Austrian Spacesuit Laboratory.
Janot, before you move on, do you hear me?
Say again?
Yeah, hello. I'm Seda, Dr. Seda Özdemir from OeWF. We would like to ask you to write your questions, please, in YouTube chat. And at the end of our tour that we are going to answer, we will have a Q&A session. I wanted to add because we...
Thank you, Seda. That's very much appreciated. I was so much in the flow here. Okay, yeah. So that's the actual machine here. So as you saw in the video before, this is where the test subject is lying down in supine position. We're going to remove that safety box here. This is just for if they drop down, they fall softly, but we have to take this out when we really go in suspension. So basically what I'm doing here, I go down here, and usually we are hooked up with lots of sensors with like ECG or breathing machines, or actually it's called spirometry. We have this type of tools you put on your mouth, and it measures your ventilatory flow, how much CO2 is coming out of this. So it looks a little bit like a fancy diving mask we're using here with all those measurement devices here. And then I go down here with my harness, lie down, and then I'm hooked up with all these cables. So this almost looks like a pulling. Actually, I could use this as a training machine. We're just realizing here. So I'm hooked up on all those cables here, and I pulled against the vertical treadmill like this. Imagine, and then I start walking. I won't do it now. It's a little bit complex to fire up the machine here. And then I'm walking exactly on this treadmill here. And this is really an amazing feeling. I can't tell you that, because it gives you this perception of actually walking on the moon. When you close your eyes and you've just watched maybe a movie about the moon, or just have a picture of the moon in front of you, this is exactly what it will feel. And this amazing moment when you start to jump a little bit higher, when you start to run, you can, if you would have lunar gravity here on Earth, it would be very bad idea, because you would be bumping your head at the ceiling all the time. By the way, if you would be living on the moon, like in a house with like 2 levels, ground floor, first floor or so, you wouldn't even need stairs, because stairs would be meaningless. If you want to go to the first floor, you just jump on it. So that's a pretty cool thing. So there's a few perks that come with my work as an analog astronaut. So that's the one thing I want to show you. This is actually a ground-based facility of the European Space Agency, operated by the Austrian Space Forum. And it's a unique facility in Europe. Actually, also worldwide, there are very few of those devices that can measure many things here so precisely. I guess what you wanted to see more is the chute, right? Shall we take a look at it? Sure. Okay, so that is it. Actually, it's a her. It's a lady. Its name is AUDA, and AUDA is not an acronym. It's actually a figure from a novel, from a famous Jules Verne novel that was called Journey Around the World in 80 Days. And AUDA is the Indian princess he falls in love with at the end of the novel. And so she's for us also like a princess. She's really nice to look at. But she's also high maintenance, like any princess, I guess. So let's take a look at that. So I'm unraveling here the cover, and that's the actual research prototype. So worldwide, there exist 2 units of this. This actually is roughly 50 kilogram heavy, takes about 3 hours to put it on, and roughly 5 months of basic training until you're allowed as an analog astronaut to work with it. It's like learning to fly a helicopter in a way. So this thing here mimics all the limitations an actual spacesuit would have on Mars. For instance, when you are pressurized, remember, Mars has a very low atmospheric pressure, about 1%, roughly 7 to 11 millibar or so. That means, for practical purposes, that's almost vacuum. That means if you would be living inside the spacesuit, you need a higher pressure. Now, if you have a higher pressure, you inflate like a balloon. And remember when you are in a fair, for instance, you have those inflatable little long balloons you can twist until you have a little dog or so with you, those ones. So the problem is, when you try to bend it, you need a little bit of force. And that is because you're shifting air volume inside the balloon. And the same thing happens here as well. So if I have the suit on, I need to make sure that every bending of a joint, like my elbow or when I close my fist, for instance, is mimicking this pressure differential as well. So we have a full-blown exoskeleton that helps us to mimic this. I'll give you one example. This is in service mode right now. So this is the elbow part. So the entire body is put into a harness. I feel like a medieval knight sometimes, where you have this elbow part, and if I flex it, there's this capsule here that is pushing against me. And this one makes sure that the elbow forces are correct and reflect the actual pressurization of the suit I would have on Mars. So, and then of course, the machine itself, there's, when you have the exoskeleton on, the underwear, the thermal control, all the electronics, the communications, so on. So we check and double check everything is important. then you're inside the suit. And that means you are actually already almost exhausted when you're just starting your spacewalk. We call this the EVA, extravehicular activity. So when you're inside the suit, you got a lot of electronics. Yeah, you have a head-up display. Maybe quick, we can show this. We can come close to the camera and go low. You should see here this black monitor. It's switched off right now, but that gives you the telemetry of your suit, the status, like how hot is in there, how's your communication status, where's your next waypoint. It could be also your own position. It could be your heartbeat that is monitored, for instance. You have external lighting, and for if you do this at night, for instance. If you want to work with little soil samples or so, it's very cumbersome to actually go down and grab something. You have little tools for that usually. And when you work with them, when you're labeling them, for instance, you have, this is a pretty cool thing here. You can actually open that part. And you have an almost empty chest pack, and it's your working surface. And this is all your control surface, where I can tell the head-up display what to do. You can plug in here like a USB microscope or other stuff, and wherever you need an instrument, you just plug it in here, and then it's connected to the spacesuit, obviously. There's a few things that are really high tech in there. We are measuring roughly 50 parameters throughout the mission. Anything from heartbeat, gas composition, and breathing air, for instance. But there's a few things that are really important because there's a human inside. And for instance, imagine the following. Yeah, you're an analog astronaut, and you're in the spacesuit, and you start to sweat because it's heavy. Of course, you have a thermal control system, but still, it is lots of load and lots of things you have to do inside. You start to sweat. One reflex we have as humans is that when we start to sweat, that also our nose starts to itch, right? And the problem is you can't really scratch your nose inside. And believe me, sneezing inside a spacesuit is a very bad idea. You just don't do that, right? But instead, we have something we call the RFD, Russell-Fresnel device. Again, if you can come closer with the suit, with the camera, you see this blue textile ribbon here. That's my best friend, because that's where I can put in my nose to rub it in, basically, to avoid sneezing. Very important. Yeah? Or imagine you are several hours on a spacewalk outside. I mean, you suddenly feel the urge for, oh, I need a bathroom break. I really need to go to the toilet now. Yeah? You cannot just go back because it takes 3 hours to put it back on again. So yes, you can go to the toilet into the spacesuit. When you're hungry, you can, or thirsty, you can drink and you can eat into the spacesuit. So everything you need for survival, at least for those few hours, is inside the spacesuit. It's your own ecosystem. It's protecting you, but also you need to protect it. It's like the Earth. We need to protect the Earth so the Earth can protect us as well. So you have your own little ecosystem right there in those 50 kilograms. And if you don't treat the spacesuit well, it will not treat you well, right? So you need to be very careful on how to work with the suit. So, of course, produces a lot of data. Those data are being transmitted via an antenna here to a base station. This is what we have here. That's what we call the operation station. This is where flight controllers sit. These are basically, it's mimicking the station on Mars. So these people sitting here are also astronauts who communicate in real time with the crew outside. So they can talk in real time. They also see the telemetry and so on. All this material, the data are being processed and then highly encrypted and go to this black box here. From there, it goes to the satellite, and from the satellite down to a control center in Vienna, where we have the mission support center. And then with an artificial time delay to mimic the signal travel time between Earth and Mars, there, for instance, our medical doctors see the ECG, electrocardiogram of the astronaut in the field with a delay. So we have to be always thinking ahead a lot when we go on those missions because of the time delay, and because also the next service center or the next replacement part is maybe 380 million kilometers at least simulated away. By the way, you are really lucky that we have this conversation today, because you only see the upper part of the heart upper torso here, obviously. But I can show you something that is also we just have it here for a couple of weeks now. We have a museum version in full glory. It's not fully finished yet. It's not the final product, but you get a sneak preview today. So there's, I think, nobody outside the Austrian Space Program who has seen this yet, and that is the museum version of the spacesuit. We have here our analog astronaut. Again, it's not fully finished yet, so it's not perfect yet. But you see basically the same technology, and this will be part of an exhibition in Upper Austria in a couple of weeks from now on in the Steel Worlds of the First Alpine Stahl AG, and you can see the thing close up. That's the reason why it's called AUDA L, because AUDA is the name of the suit, and L stands for Linz, which is the city where it's being displayed in. By the way, fun fact before we move on to the last part, I said AUDA is a princess, like this Jules novel figure, huh? And because she is a princess and we have a lot of superstitious traditions in the space flight, there's also one thing that always goes with her when she's traveling, because she is a lady. And a lady always, in our case, traveled with a rose. So this is the box where the spacesuit is being transported, part of the spacesuit is transported. And when we go into the field, she goes with a rose because she's a lady. So, little tradition to have. All right, so these were simulations so far, right? This is what we do when we go to Mars-like areas on this planet. How about actually going to space? Well, we can do this here as well. So what we're going to do now is we're going into the integration room of the Austrian Space Forum, briefly for a couple of minutes. And you follow me? You really get to see some really cool stuff today. That's not something everybody gets to see. So, all right. So this is the integration room. That's the office part of it, and that's the actual part where it needs to be a little bit cleaner when we go inside. This is a place where we actually build stuff for spacecraft. I've here a little model, and we can get a little bit closer. That's the, what's called the Adler 1 model. It's basically a 1-to-2 model of a CubeSat that was flown a couple of years ago, looking for microspace debris. Now, to explain this, space is not far away from us. So if you think of it, the Earth has a diameter of 12,500 kilometers. The ISS is in an orbit about 400 kilometers above the surface. So it's just scratching the outermost layers of the rest of the residual atmosphere there. So most of the satellites that are relevant for our daily lives are either in geostationary orbit, like television satellites, for instance, but all the communication satellites, a lot of the Earth observation satellites, for instance, they are at much lower orbits, around 500 kilometers or so. Now, we see in the last 10, 15 years, an exponential increase of satellites up there. But it's not only satellites up there, but it's also burned out outer rocket stages. It's uncombusted rocket fuel. It can be flakes of paint. It can be micrometeorites from outer space. So there's lots of rubbish out there, right? The problem is those particles might be small, and this looks like harmless particles. The problem is they are tremendously fast. And when they come in with 20, 30,000 kilometers an hour, I mean, they're getting really big speeding tickets, I guess. Yeah? They can develop a lot of damage. And that is because if you think of the formula that defines kinetic energy, mv squared is half, so mass times velocity squared divided by 2, if you double the velocity, you quadruple the kinetic energy. And so a part of a flake paint, like a 1 millimeter particle, that is a totally harmless paint flake here on Earth, if that hits you with 25,000 kilometers an hour, it's like a gunshot. Huh? And so we need to assess the problem out there, how many particles are in that orbit. And boy, it is messy. We humans really have the talent that wherever we go, we take rubbish with us. And that's something that is not fully cleaning out itself. It is an emerging problem. So space debris mitigation and avoidance is a very big, important topic in spaceflight. So environmental protection does not stop at the top of the atmosphere. It actually goes beyond. And this little satellite is measuring that. You see here the core part with where you have the energy supply, the computers and so on. You have the solar arrays that gives you power. And then you have this little accordion thing here. It's just a symbolic model here. It's actually a foldable mechanism that allows you to detect little particles. So if there's an impact of a little particle, there's a little bit of an electrical signal created with a piezoelectric element. So this acoustic shock wave is translated into electronic signal. So basically, this thing here is, be with me, a microphone in space. Usually say you can't hear anything in space. Well, the material itself can transfer, of course, acoustic signal. So let's have a look at this, how this really looks like. And I'm going to put on something very important, very, very modern, very trendy. I feel like I cook a little bit. I'll keep for later. I'll put on my jacket here. This is a laboratory coat that is also helping us to avoid electrostatic charging. That's the reason why I have these little lines in here. These are actually conductive threads. So when I touch something, I do not destroy anything. Again, taking off jewelry has nothing to do in space. And then in the last part, I'll just put on our overshoes. And unfortunately, camera has to stay out, but I will show you through the window here. The good thing is you can still hear me via the headset, I guess. So lots of electronics here, obviously. I'm going to show you a part that is the real thing. It's the engineering twin of one of the wing elements you just saw before. Actually, it's from the second generation Atlas. It's not the very same satellite, it's the successor satellite. And I'm gonna touch it here, in the frame here, so I don't have to touch it directly. And so actually, this is a part of a satellite. You see this pattern here, it's actually, there's a hidden message in this. So basically, we have a little circular discs in there, in those layers in between the PCB. And if then something hits you, then it gives you a signal, basically. And the signal comes out here, this little, well, where the cables will be fixed in, of course. And so you have to think of this as one part of a much larger wing. So it's basically folding out like a concertina in space. And you have about 2 meters length of coverage. And this is our microphone in space, basically. And well, if you're really good in Morse code reading, if you go to the website, you have the full picture there of Adler 1 and Adler 2. Sorry, 2 has this picture. There is a hidden message in there. Nobody has deciphered it so far. It's not trivial. Let's see if somebody is the lucky one to find out what's written in there. Okay. There's a few fancy things in here which are not easy to show because they are behind this wall, so you cannot see them. But I think that's okay for now for this part. And of course, as you see, lots of 3D printing. That's very important in spaceflight as well. So let me get back out again. So, there you go, here as well. And then we'll head back to my office. And I'm going to show you that space exploration is not only for adults, it's for young people as well. Okay, I'll go back to the video and we can actually switch off the mobile phone video here. And I go back to video. All right, okay. We just need the audio signal, Selina. Perfect. All right. So I'm gonna show you again a few slides here, which are pretty cool. I just mentioned before that space exploration is not only for old guys like me, but they're for everyone. And so I want to show you an example of how this works by talking like 2 or 3 minutes about the Explorer program. So both our research organization and wonderful partners across Europe, Nucleo in Portugal, EA in Greece, COSPAR in France, and other organizations have been joining up to involve young people in space exploration as well. And so we have set up a program called Expeditionary Program for Learning Opportunities in Analog Space Exploration. By the way, you can also, if you're a teacher or in the class, you can always sign up to this. It's easy to find, explorer-project.eu, and easy to find online. And what we did basically is we took teenagers, literally teenagers, 16, 17 years old from across our partner countries, trained them well over the duration of roughly half a year in parallel to doing their school. And then they were forming a team of students from 3 countries, Greece, Portugal, and Austria, to mimic a Mars simulation here. So it's a simulation of a simulation, so to say. But boy, it was really, really getting close to the real thing, I can tell you. So we actually, after training, we flew all the students to Portugal, to Montserrat, which is a fantastic area also for observing the night sky at the observatory Lago de Alqueva. And there we built a station and rooms that were somewhat similar to what we have during our own professional missions, also with simplified spaces. So these don't weigh 50 kilograms, and no, it don't take 3 hours to put them on. So they're quite simplified. And people will then go out on extravehicular activity, work together with robots, for instance. And for 1 week, they would be working as real analog astronauts. And I think it was both for us and the young people an amazing experience. The project is still ongoing. We have another mission plan for April next year. And there is a new project called Sphere coming up that is focusing on the similar topic, and there will also be missions in Montserrat as well. So all those 3 projects, the Sphere, Explorer, and STEMMOS, they go hand in hand. They are a part of a much larger undertaking of bringing space into the classrooms, bringing space really into the hearts and minds of people. Then, because I can promise you, whatever it is out there, planets like Mars or the moon, there are wonders and miracles out there yet to be discovered and yet to be explored. And your generation is the one who is doing these actual steps. We, the older ones, we're preparing for you. We are the ones who are building your ships and make sure that you have a safe and scientifically productive journey. And having said that, I wanted to mention also last time that especially for the STEMMOS project, if you're interested in following on this, there is a website where you can register as well. I would really, really urge you to register there, to follow, maybe even get involved in a way, maybe take a look at satellite imagery of other worlds, of our own world, of the Earth, of course, and stay tuned in what students of your age might be doing. And maybe we can put this also into the chat here so that everybody has a chance to have the link directly clickable. And if you really want to do me a favor, right at the end of this or right afterwards, please go to the STEMMOS website or the Explorer website and register there. You're doing us a favor. It's a win-win for everybody involved. Having said that, I would like to conclude my presentation part, and I would be thrilled to take questions both from the live stream or from the Zoom call here. I do understand that in the live stream, we are, for technical reasons, delayed by almost a minute. So I'll give you a little bit of time to also type questions. And then Gustavo said I will be relaying questions to my location. I will try to address them as to my best abilities.
People are very quiet on the chat, so...
Oh, everybody's
yeah, but we have the people who are more vocal here. Isabella Churea, she's from Romania. And also Arista Paul from India. So we have a pretty international audience here. But you need to be more vocal. Put your questions on the chat so Gernot can answer. Yes.
Please, you can ask me anything. This is your chance to ask anything of how do you go to the toilet in 0G to other aliens, anything. It can be related to the spacesuit laboratory, it can be related to the spacecraft engineering part, of course. It can be career related, like how do I get involved in space professionally? What can I do after I graduate from high school? It could be like, what does it feel like in the spacesuit? Anything. So this is your chance for one-on-one questions, and I'd be I'd be thrilled to take questions from you. Don't be shy.
Yes. So meanwhile, Gernot, while we wait for the questions, because of the delay also, it's good to reinforce the invitation for all the people that are watching to join the STEMMOS project. So we have the link to the project on the chat as well. And also for the teachers to register in the portal, that where we will find all the activities and resources and training courses on the observation of the Earth, Moon, and Mars.
I think that's an important thing to mention, especially for STEMMOS. Registering is not signing up for a newsletter only. It's about getting access to educational materials that are of high didactic quality, that are for free, that are up to date, that are really reflecting the state of the art in Earth observation research and planetary observations. And it's really a wonderful set of tools for various levels of ages, for various focus, if it's more life science, more physics involved, or so. Can also be other classes involved. Why not having an art class about the beauty of Earth observation, of seeing natural processes from space. So there is a natural painting, a set of paintings out there because of all the Earth observation images, for instance, or a language class where you think about how to, what should be the first words that are spoken on Mars by humans? What do you think people will be dreaming of? So it really gives a tremendous decision-making space for inspirational stuff as well. For all you teachers out there, why not consider for the next exam or a test or so having a space-related topic? Why not joining up with research teams from your own communities, for instance? We're happy to also lay out links and write letters. So this is really something where we would like to see people engage and be involved. I can tell you from my own experience, it's an amazing type of work where we're privileged to witness here. Working in space means that you're working with usually very intelligent people who are incredibly dedicated and love what they're doing. I don't know a lot of other fields where this amount of dedication and this enthusiasm is so strong, like in the space field, because after all, if you're working on Mars exploration missions, you are part of the most ambitious and longest journey we've ever undertaken as a society. And being part of this makes you big as well. And that's something I really, really recommend in many ways.
Okay, so we're still waiting for questions, Gernot, but we have one more hello here on the chat. That's from Marlene Serra from Portugal. So welcome again.
Yeah. Hello.
Yeah, so she's also a participant of Explore. So good
awesome.
to have the Explore crowd aboard.
By the way, just as a fun fact, Portugal is also participating in the world's biggest analog starting next week on Monday. I haven't mentioned that yet because I talked about so many projects already, but just as a fun fact, next week for 2 weeks, we're going to have an extraordinary simulation. So coordinated by a mission coordination center in Vienna in Austria, we are going to have 17 habitats, base stations, either on Mars or the Moon and one spacecraft in transit, spread across 5 continents on this planet, on Earth, where we mimic a future where we're not talking about the first humans on Mars, but we're talking about the first groups of humans on Mars and on the Moon, just like Antarctica is now settled with a couple of stations. We are going to see the same thing happening on the Moon and Mars as well. And this is going to be an incredibly exciting adventure, I can tell you. And I also hear that we have visitors from our audience from India. India is also participating in this. We have stations in Kenya, Brazil, in Portugal, in Poland, in the United States, in Jordan, in Oman, in India, I mentioned already. So it's really across the world, and it's quite a unique undertaking where we're going to have a very steep learning curve for sure.
And Gernot, it's good to mention also we are going to visit the Mission Coordination Center.
Yes, absolutely. So next week we're going to have a live link for everybody interested right at the opening ceremony of the world's biggest analog. So next week on Monday, that'll be at 8 o'clock UCT. That corresponds to 10 o'clock CEST, like Vienna or Berlin time, for instance. That'll be 11 o'clock Lisbon time for comparison. And so this will be roughly also a little bit less than a 1 hour live link from the Mission Coordination Center. You will get to see the control rooms in live in action. And if I understand it correctly, Seda will be hosting that event. And if we are nice to her, she will bug some of the flight controllers and the flight directors, the director of operations there to be there for your questions and answers as well. So it will be a highly international event, and I would love to see all of you there as well.
Gernot, we have a question now. Sorry to interrupt, but we have a question from Arita from India. Asks if the astronauts have to throw away the suits once they wear it after they're back from the mission. I mean,
yeah, well, not all of it. There are some parts that are exposed to the external environment, like the dust and the abrasive. So if the outermost layers of the spacesuit are not tight enough anymore, those can be exchanged. But all the interior parts, like in a diving suit, like the atmospheric gas processing, the board computers, the batteries, the sensoric network, and so on, all of this can be reused. They did the same for the space shuttle spacesuits and also the ISS spacesuits, for instance. It's just that the refurbishing of a suit is quite a long undertaking. So for the shuttle suits, it took several months until this process was concluded. They could not do it for the Apollo missions. The Apollo spacesuits were really single mission, single use spacesuits, but that was also because they were customized to the respective astronauts. We have now a more modular system, so we can accommodate short legs, long legs, for instance. So we're going for something that is more sustainable, I would say.
Thank you for the question, Rita, and for the answer, Gernot. Very interesting. Have another hello here from Teresa Souza, which is a well-known teacher here for our group, also participating in Explore and STEMMOS. So she sends you greetings from Portugal and their students.
Hey, thank you.
Okay, we're still waiting for a few questions, so maybe Gernot, if you can tell more about WBA, what we're expecting.
Sure. My pleasure. And if there are no more questions, we can also conclude any moment or so. We don't have to spend the full hour, of course. Yeah. But maybe there's a few other cool things that are related to the WBA project, and that is it's the first time that this is happening. So this is we are having roughly 10 WBA specific experiments that are running from human factors, geoscience, biological sciences, for instance, astrobiology. But I think besides those experiments, which are the heart of our missions here, it's also the fact that we are learning how to talk with each other. We have, 17 habitats involved. That means we have 17 different cultures, languages, people's mindsets, lots of disciplines that are involved as well. And it took us about 2 years to really learn to talk with each other and have homogenized communication, decision-making workflows. So this is one of the things that was most interesting for me to understand, that after so many years that analog research has been around, this, to our surprise, was the first time anybody thought about that. So there was an initiative from Jess Purewell from United Kingdom, together with some colleagues from the US, who had the idea of, how about if we pull together all the stations, or most of the important stations that are around on this planet, and have also agencies involved. And then they say, well, we need some sort of coordination facility that is able to handle all this traffic, that is able to take decisions, have the workflow, the mechanism for that, the people for that. And so they approached us as the Austrian Space Forum and said, well, hey, would you be up to the challenge of hosting, 5 habitats, 6 habitats? Maybe it's 10 or so. That was our planning bases at the beginning, and now we're ending up with 17 habitats. We had to already put a stop to this to not have more ones involved, because just imagine being a flight controller in the Mission Coordination Center, the operations room, as we call it. And you're, throughout the day, you're mentally jumping from Earth to Mars, to a spacecraft in transit, from India to Australia, to Oman, to Brazil or so. So you need to make sure you're really mentally in the right place, because your readout of the telemetry and the subsequent decisions that are being taken, they have consequences in various locations across the world. So you've got to be very focused to make sure that you really have, that you're mentally in the same habitat like you're talking to at this moment. So it's got to be quite an exercise for all of us. So we had to split up into several trails of communication with different, we call this Earth comms, that are able to talk with the people with very regulated protocols, and still make sure that we have a minimum amount of situational awareness of what is happening in the station, if there's a CO2 buildup, for instance, or so. So lots of high tech obviously involved, but we are also doing a number of pretty interesting other experiments. For instance, we are tracking trash. So when you think of 6 people going to Mars, for instance, they will produce over a year, that this rough number of how the mission will take or so, they will take a lot of stuff with them, and a lot of this will be trash. And this trash is a resource. And the question of how can you reuse that, how can you recycle it, how can you upcycle some stuff, that'll be a really interesting question. But for this, we need numbers. And these are the type of projects where we get those numbers. Another interesting thing is, well, you might have the time delay communication with Earth if you're on Mars, but it does not apply to the other stations that are on Mars. That means we can allow for Mars to Mars local calls in real time. So the level of feeling being alone on Mars will be very different if you have other stations there, although they could be like thousands of kilometers away, but still they're on the same planet. They're still in real time communicating with you. So I am wondering what type of stories and problems and solutions and support those stations can give to each other. Nobody tried that before. We simply dive in to see what happens. That's the beauty of it. We are literally entering new ground with this type of research. And so I can tell you, I'm quite thrilled. My mind is on Mars and the moon since a couple of weeks, because we're just before the mission start right now. And the enthusiasm of the team is incredible. I mean, those people, they are really top of the line working here together.
Thank you, Gernot. It's really very exciting. People are quiet, so maybe we should wrap up the questions, unless there's a question arriving now. Just a reminder for the teachers that are watching here, we have also schools from Greece and Ireland to fill in the attendance form. The link was sent by email, so we can have at least everyone that attended. This is very important for the projects as well. So apart from that, I think maybe you say farewell, and there will be other visits. There's another one today, this afternoon, at 2:00 p.m. Central European Time. Another one tomorrow at 9 a.m. Central European Time. And finally, the visit to the Mission Support Center that will be next Monday. So there's still time to register, and we hope to see you, more people joining the visits during the week for the World Space Week.
Thanks, everybody. On to Mars.
Mars. Thank you.
Thank you.